Okay, so we are entering the fourth video for this chapter, at least in this series. We are looking now at a subtopic called um, charges in uniform electric field. Okay, so what we're going to do is just going to take a charged particle and then put it in a uniform uh, electric field and then work out its kinematics. All right, so main thing is that you have to remember your kinematics equation, and I'll demonstrate that through a few questions. Okay, so what we want to do is we want to look at this question, problem 1. The figure below shows two metal plates with a potential difference of 3 volts, so there's 3 volts between them, separated by 50 centimeters. So if you were to find the electric field, right, between them, you will simply calculate it by having V equals to ED. All right, so V equals to ED. So that means that my electric field strength is simply going to be V over D. That means it's going to be 3 over 0.5, which is 6 Newton per Coulomb. So that's going to be my electric field strength. Okay, let's continue on reading the question. An electron is released from the negatively charged plate. Calculate the acceleration of the electron. So if we would talk about acceleration, we have F equals to ma. This is from Newton's law, right? But from electrostatic, we also have learned that it's also equal to QE, right? So I'm doing the first part, the acceleration part. So then if I were to find A, it will be QE over M. The good thing is, because we're talking about an electron, we know the charge and the mass of the electron. Okay, so the charge of electron is 1.6 times 10 power of negative 19, and then we have the mass of the electron, which is 9.1 times 10 power of negative 31, and then of course the electric field, which is just 6. Okay, so then my acceleration is, let me check, you can key in the calculator while I check, you will get it as to be 1.055 times 10 power of 12 meters per second, and that is your acceleration. Okay, now after that we are expected to calculate the kinetic energy of the electron just before it reaches the positively charged plate. So there's two equations that you need to know here, right? Kinetic energy is just half mv square, and from kinematics we also know that v square equals to u square plus 2as. S just being the distance that it has traveled. Okay, so the good thing is that the electron is released, we assume that it is released from rest, so it's going to be 0 here. So then I'm left with v squared equals to 2as, and that gives me kinetic energy is equal to half m times 2as. So then my kinetic energy is going to be half, sorry, not half, because the 2's cancel. So the 2 cancels, and I'm left with m times a times s. Okay, and the mass of electron, as we've seen before, is 9.1 times 10 power of negative 31, and then times the acceleration, which is 1.055 times 10 power of 12, and the distance that it has traveled, which is 0.5 meters. That would give me a kinetic energy of approximately 4.8 times 10 power of negative 19 joule. Okay, so that is going to be my kinetic energy. So that's my kinetic energy, and this is my acceleration. Okay, we'll do more questions like this in problem 2 as well. Okay, so moving on to question 2. Okay, so let's look at this question. The figure below shows an electron entering a region of uniform electric field at 5 times 10 power 5 times 10 power of 6 meters per second. If the magnitude of the electric field is 200 volts per meter, calculate the acceleration of the electron and the vertical displacement of the electron when it leaves the region of uniform electric field. Now, so what happens is when the electron enters the region of electric field, it's going to start to move towards the positive charge plate. So then we get this deviation, right? We get this deviation which we can call Sy. So that's what it means by the vertical displacement. Okay, so let's look at the first part of the question, which is relatively easier. I have F equals to ma, which is equals to QE, right? So then quite easily I can say that the acceleration is simply going to be Q over m times E. Again, as we've seen in the previous question, let me just show that again. In the previous question, my Q is just 1.6. It is a constant. So 1.6 times 10 power of negative 19 over 9.1 times 10 power of negative 31. And then my electric field is just 200. Okay, so then what we get is going to be 3.52. So A equals to 3.52 times 10 power of 13 ms negative 2, and that is going to be my acceleration. That's the answer for the first part. Okay, so equate it to Newton's law, F equals to ma, and then that's what you get. All right, okay, so moving on to the second part of the question, the vertical displacement. All right, so what I need is I will need to have equation for Sy. And quite simply, I can have uy t plus half ay t squared. Again, here we're ignoring gravity, okay? So my yg is going to be 0. Just assume that for now because it doesn't mention anything about gravity. And then my initial velocity and my final velocity. Now, my initial velocity in y is initially at 0 because this 5.6 is only in x direction. Okay, so then my Sy becomes half times ay t squared. Where do I find t squared? Well, if we look at Sx, okay, if you look at Sx, you will find that it is actually equal to ux times t. The good thing is the amount of time that the electron takes to exit this region is also the amount of time that the electron takes to move by Sy. Okay, so then Yt is simply Sx over Ux, and I can substitute that. I can substitute into my initial equation, which is Sy equals to half Ay times t squared. So I'm going to have Sx over Ux. Okay. All right. So then we have calculated that value before. I will have half, then Ay is 3.52 times 10 power of 13. The horizontal displacement is 50 centimeters, so that's going to be 0.5, and my initial velocity in x is 5 times 10 power of 6. Okay, so if you key that into your calculator, you will find that this is actually moving, it will actually move by 17.6 centimeters. So that is its vertical displacement. So I just want to emphasize again that in this part of the chapter, you actually have to know kinematics equation as well. Okay, so moving on to problem 3. Here we have a charged particle of charge 2 microcoulomb suspended between two charged plates of potential difference 20 Kelvin separated by 20 centimeters. determine the mass of the charged particle. So again, it's always useful to just draw it out. What you're going to have is a negatively charged plate at the top, and then you're going to have a positively charged plate at the bottom, and then you have the charged particle, and then gravity moves downwards. So if you were to draw the force diagram, you will have Fg moving downwards, and then Fe moving upwards. Because it says the word suspended, my Fe must be equal to my Fg. And I can quite simply substitute for equation. I will have QE equals to mg. I would like to remind you that E is just V over D. Okay, V over D, and then I have mg. I can rearrange that. Mg equals to, sorry, M equals to QV over dg, where my Q is actually 2 times 10 power of negative 6. I have my V to be 20,000. I have my D to be 0.2, and I have my G to be 9.81. Okay. All right. So if you were to key that into your calculator, what you will find is that this object will actually have approximately 20 grams as its mass. Okay, so for this particular question, it's just useful to just draw out the force diagram. Okay, moving on to question 4, problem 4. A 2 microcoulomb charged particle of mass 3 microgram is released from rest in a region of uniform electric field of 80 kilonewton per coulomb, as shown in the diagram. So, okay, fine. And then it then moves 50 centimeters towards the negatively charged plate. Determine the potential difference between its initial and final position. So again, I have V equals to E times D. So my V is just E, which is 80,000 times D. The distance traveled is 0.5, and that would give me 40,000 volts. Okay, so that's the potential difference. And then the change in potential energy. If I were to find the change in potential energy, all I need to do is to find, sorry, this is delta V, is to multiply the charge with the potential difference. We are given the charge, which is 2 times 10 power of negative 6, and then the potential difference is 40,000 volts. All right. If that is the case, then the change in potential energy is 0.08 joules. Okay, so now the potential energy has been used up, right? And it has been converted into kinetic energy. Okay, the kinetic energy, the change in energy, is just half mv square minus half mu square. But because it is released from rest, your initial kinetic energy is 0, right? And all of this is equal to delta U. So then what I'll have is I will have half, then times 3 times 10 power of negative 6. So that is 3 microgram, right? And I'm looking for U. And my delta U is 0.08. So V square. I'm looking for V square. So then if I just calculate that, I will have, so let's see, I will have 2 times 0.08 over 3 times 10 power of negative 6 square rooted. I will have a velocity of approximately 231 meters per second. And that is my final velocity. So as you can see, even the concepts of work and energy has been used in this kind of situation. All right, so even though we're talking about electrostatics and electric fields and everything like that, but then we do have to remember our kinematics as well as our dynamics and work energy theorem as well. All right. Okay, that is all for this video. Thank you very much.